Now in this class we will go and understand what are primary quantities and secondary quantities. Okay. Look at here. First, what do you mean by primary quantities? Primary quantities, or you can say fundamental dimensions. Fundamental dimensions. Okay. And later we will study what are secondary quantities. Secondary quantities. Okay. Next, or otherwise the secondary quantities are called as derived dimensions. Derived. Okay. Derived quantities we can call. Derived quantities. Right. Fundamental quantities are those which are very fundamental. For example, this mass is there. That mass is measured as what? Mass is measured in terms of kg, measured maybe in grams, in tons, okay, or it may be in quintals, okay. Like that, mass can be measured in these parameters by using these dimensions. Then we have length. Length is the parameter that is measured in terms of meter or kilometer or centimeter or feet or inch, or inch or yard, okay, like that. It can be measured in many forms. Okay. Now we have another very fundamental parameter, that is your time. That is your time. Time can be measured in terms of seconds or hours, days, years, like that, decades. This time can be measured this way. But these three are these three are there here: mass and length and time. These three are very fundamental. Means in this universe, whatever you take, whatever the mathematical format or mathematical symbol you take, or parameter or quantity you take, and all the parameters you have to fit by these three only. That is your mass. In terms of mass you need to measure, or in terms of length you need to measure, or in terms of time you need to measure. Okay, you cannot escape from these three. And nowadays that international standard is included one more dimension to this fundamental dimensions, that is your temperature. Temperature is also an independent one. Okay, it is an independent parameter, and the temperature is measured in terms of degree centigrade. Okay, therefore we will consider it as a theta, degree centigrade. Understood? And what are the secondary quantities or derived quantities? Means your velocity is there, acceleration is there, and force is there, viscosity is there, dynamic and kinematic viscosities are there, our area is there, our volume is there. See how this area is measured? Area is measured as meter square, or I can say area is measured as length square. Length square. See, you used this fundamental quantity two times, that is length into length. Then how volume is measured? Length cube. Length cube. See, this length you are using cube, that is a volume you will get. Then how to measure this velocity? Velocity is the length covered by distance covered by time. Then length and time you are using. This and this you are using. Length and time you are using. Like that. What is this force? Force is a mass into acceleration, means you are using mass. See, you are using mass. And acceleration is measured as meter per second square. You are using length, then you are using length. You are using second, time, you are using time. See, these all parameters: velocity, acceleration, force, viscosity, area, volume, these are all called as secondary quantities or derived dimensions, derived quantities, because these are derived by using these fundamental properties, fundamental dimensions. Okay, and how these dimensions are used, we don't know. They are independently, they are there. That is very mystery. You need to understand what you mean by 1 kg. Why it is called as 1 kg only? 1 meter distance means that much. Why it is called as 1 meter means that much only? A second we will measure it as a tick. Then why that tick is considered? How that is considered as 1 second? Who agreed with these concepts? Who agreed that saying this is 1 meter? These are all the things you need to study. They are very fundamental things. For this chapter you should know only this information, that mass and length, time, temperature are fundamental quantities, and the other quantities which are derived by these are all called as derived quantities. Understood? Now when you come to international standards of this dimensional analysis, they say that mass we will call that as a capital M, and length fundamental quantity we will term it as a capital L, and time we will call it as a T. Okay, and temperature we will measure it as a theta, and these are all very important alphabets in dimensional analysis. The meaning of M indicates mass, the meaning of L indicates length, the meaning of T indicates time, and the theta is the temperature. And dimensions always we need to write in a square bracket, that is M L T, means it is maybe like a meter, sorry, kg meter second. And if you write M L T raised to minus 2, then it is meaning that kg meter per second square. See, T raised to minus 2 means time comes down, time square. Then if you want to measure meters cube, then it will be, its dimensions will be L cube. Understood? Like that we need to understand. And some derived quantities now only I will teach you, so that in further when we start the chapters, there it will be easier. You can consider directly the derived quantities, derived dimensions, and go ahead. These dimensions might be studied in your PU, pre-university courses and all. We have a geometric dimensions. For example, we have a area. Area is a geometric dimensions. It is unit is meter square. Therefore, it's a length square. We can call it as a length square. Therefore, its dimensions is L square. Like that. Volume. How you measure volume? Volume measured as a meter cube, and a length cube. This is a length cube. Therefore, it is dimensions is L cube. Understood? Like that, moment of inertia is there. Moment of inertia unit is m power 4, meter power 4. Therefore, it is nothing but a length power 4. Dimensions we will call it as L power 4. Right? We have some other quantities like kinematic quantities. Okay. The kinematic quantities are like this. Kinematic quantities. The first one is velocity. Velocity, you already know, velocity unit is meter per second, or you can call it as a distance traveled. Distance traveled in a particular time. Therefore, distance is measured as a length, and time is a t. Therefore, the dimensions can be written as L t raised to minus 1. You need to write in a single line. Okay, and then we have a acceleration. Acceleration, we have that acceleration is rate of change of velocity. The unit is meter per second square. Unit is meter per second square. Therefore, meter means it is a length, and time minus 2. This is your dimension. Okay, like that we have a discharge basic equation, Q equal to A into V. If you don't remember this, at least you should know what is the discharge unit. Unit of the discharge is meter cube per second. Then meter means it is a length, therefore it is a length cube, divided by second is a time. Therefore your dimensions is L cube t minus 1. This is your discharge. Understood? Like that we have a kinematic viscosity. First we will study dynamic viscosity. Dynamic quantities, in that one dynamic viscosity. Dynamic viscosity, if you know the unit directly, that is Newton per meter square second, we can call it as a Pascal second. If you know this much, that is also enough. If you don't know this one, then go to the basics, that is shear stress is equal to mu into du by dy. You studied in fluid mechanics, where mu is equal to shear stress divided by du by dy. From this also you can get this unit. Say for example, this Newton per meter square shear stress, and velocity is meter per second, and this is 1 by meter cancel, Newton per meter square, yes comes to the top. Therefore this is the unit that you can call it as a Pascal seconds. If you don't know these all equations, at least you should know what is the unit of dynamic viscosity, that is Newton second per meter square. Then how to write the dimension for Newton? We don't know. Then Newton is a force unit is the Newton. Then force is a mass into acceleration. Mass symbol is m. Acceleration already known in a previous slide, that is L t raised to minus 2. Then this is your force dimension, that is your m L t raised to minus 2 is a force dimension. Means in the place of Newton I can write this. Then what is your dynamic viscosity? Dynamic viscosity equal to m L t raised to minus 2. That is your n, and divided by meter square, that is L square, and into time. Then your answer is, this L square comes to the top, minus 2, or L cancel, minus 1. Therefore m L raised to minus 1 and T raised to minus 1. This is a dimension of dynamic viscosity. That is your dynamic viscosity. Then if you know dynamic viscosity, you can kind of find out the kinematic viscosity. Kinematic viscosity is what? Dynamic viscosity by G. G is a sorry, not G, this is a rho, and mu we know that is a dynamic viscosity, m L minus 1 T raised to minus 1, and rho, the unit of rho is what? Rho is kg per meter cube, kg per meter cube. Therefore the rho dimensions are meter length minus 3. Therefore if you write here, that is dynamic viscosity is a m L raised to minus 1 T raised to minus 1 divided by m L raised to minus 3. Then it will be m cancelled m cancelled, and L 1 cancelled. Therefore it will be L square T minus 1. Am I right? L square T minus 1 is a dynamic viscosity of dimensions of kinematic viscosity. If you directly know the dynamic viscosity, kinematic viscosity unit, then what is it? How the kinematic viscosity is measured? It is measured as meter square per second. And if you know this one directly, meter square is a L square, and per second is a T raised to minus 1 over. This is also good. Okay, you can come by basic equations, basic parameters, and substitute in that and get, or otherwise directly remember the unit of the parameter, and after that substitute the MLT corresponding to that, then you will get the dimensions. Like that we have many, for example, density, specific weight, dynamic viscosity, pressure intensity, modulus of elasticity, surface tension, shear stress, work, energy, power, like that many are there. You need to try for them with the basics and by knowing their the units. Okay, just refresh what you studied in the previous, or otherwise whatever the parameters I told now, those are all, make a list and make a dimensions of them. Okay, this is enough for the today, and next class we will go to the methods. First we will understand dimensional homogeneity, then we will go by this release method. Thank you. Dimensional homogeneity. Okay, dimensional homogeneity. Dimensional homogeneity means it's just a simple that every equation we will be having LHS and RHS, right? Every equation means what? It will be having a equal signs, and equal sign is there means left hand side something will be there, and right hand side something will be there. LHS and RHS will be there. Okay, if I write the dimensions of LHS, that in terms of M, L and T, if I write the dimensions of LHS side, that is in terms of M, L and T, in the same way, then whatever that is the parameters are there in the right hand side, for all of them, if I express them in terms of M, L and T, then they must be equal. They must be equal. Or I can say that the powers of this M and this M must be same. The powers of this L and this L must be same. The powers of this T and this T must be same. Then I can say that the given equation is dimensionally homogeneous. Okay, the dimensionally homogeneous. The simple thing. The definition, you can call it the dimensional homogeneity, means dimensions of each term of the equation in the bracket, left hand side and right hand side, close the bracket, must be equal in their fundamental powers. Okay, then in explanation you can write that each and every equation will have a left hand side and right hand side. Independently, left hand side if you express that parameter in terms of M, L and T, and right hand side if you express those parameters M, L and T, then the powers of left hand side and right hand side fundamental quantities must be equal. Then that is called as dimensional homogeneity. One example I will show you. Check whether V equal to root 2GH is, what is the question? Check whether V equal to root 2GH is dimensionally homogeneous. Okay, they are asking to check. Okay, first LHS equal to RHS I will write. Then what is LHS? LHS is velocity unit is meter per second, and its dimension is L T raised to minus 1. Correct? Then this is call it as equation number 1. Then what is RHS? RHS is root 2GH. Okay, means I can write it as a 2gh to the power 1 by 2. Okay, now then 2 dimensionless and g is a acceleration meter per, so you can write it like this, L t raised to minus 2, right? Then h is a length, that is L, therefore you will get a L square t raised to minus 2 to the power, means this all entire power 1 by 2 is there, to the power 1 by 2. This 1 by 2 multiplied to L, then it will become 2 to cancelled and L will be left, and this 1 by 2 multiplied to minus 2, then it will be left minus 1. Now see, this equation number is 2. Then the equation number 1 and equation number 2 are same, L t raised to minus 1. Therefore I checked it. Therefore V equal to root 2 GH is dimensionally homogeneous. Understood? This is what they are giving they are explaining what is homogeneous. Okay, dimensional homogeneity. Now coming to methods of dimensional analysis. Methods of dimensional analysis. How many methods are there? Actually speaking, there are many methods are there, but for your syllabus we have that VTU is included 2 methods. The first one is, that is the Rayleigh's method of dimensional analysis, and the second one is Buckingham's method, Buckingham's pi theorem, which is called as pi method, you can call. Okay, these two are included. Okay. In this class I will just explain how Rayleigh's method is worked out, and in the later classes I will explain the procedure, or otherwise I will consider some problems and I will explain Rayleigh's method. See, this Rayleigh's method is very simple. First I will tell you, when we go for Rayleigh's method, or otherwise dimensional analysis, when we want, why we want this dimensional analysis, you should know. Say for example, I have some parameter with me. I would like to know here that in a water, if I throw one steel pebble, then it will go down, right? Then what is the velocity here? The velocity of the steel ball which is moving inside the water, how it is affected, whether it is affected by some other parameters, that I would like to know. Okay, think that if this is a vacuum, and here you drop a steel ball, then measure the velocity, and later you drop here and measure the velocity. Both are not same, because here some resistance will be there. Then what are the factors which are resisting your movement of the steel ball? Then I can say that the density of the water, yes, density of the water is a parameter which is resisting your movement, and I can say that viscosity of the viscosity of the water, that is also resisting the movement of your glass ball, and I can say the drag force is offering the resistance, and say your gravitational is not resisting, but it is supporting, it is supporting the movement. Okay, like that, this velocity of the glass ball moving in the water is depending on so many parameters. Whether they might be directly depending or inversely depending, we don't know, but they are depending on these many parameters. Then the question here is how we need to establish the relation between them. Then how I have to write? V equal to rho nu f by g I have to write, or V equal to g rho into f to the power 1 by 2 square. Then how I have to write? I don't know. Can you make an equation out of this V and these all parameters? That is very difficult thing. Therefore this dimensional analysis chapter is introduced. Here you will get a rough idea how these parameters can be related to the velocity. Understood? The same way here in the Rayleigh's method, we will be having two variables. The first one is dependent variable, and the second one is independent variable. What we do, this dependent variable, if I call this is a x, and this x is depending on so many independent variables, they are small x's, so many independent variables. Then how I have to write a general equation? Then x is a function of x1, x2, x3, like that, xn. See, this x is there, no, this variable is depending on many other variables. This is a generalized equation. Okay, in some textbook they will write it like a f of x1, x2, x3, x4, like, or otherwise even you can write it like x equal to k into, k is some proportionality constant, then k into x1, x2, x3, x4, okay, xn. This is a Rayleigh's method. Then what is the procedure, how to solve the problems of this Rayleigh's method? The first one is identify which is LHS and which is RHS. First identify, I will write neatly that first procedure of Rayleigh's method solution is first identify LHS and RHS. Okay, write all the dimensions of LHS and RHS parameters independently. Okay, na? First you know already fundamental parameters, you write them. First you write LHS parameters and RHS parameters, you write all dimensions of LHS and RHS. Okay, the third point will be express LHS and RHS in this format, that is x equal to f of x power a, x1 power a, x2 power b, x3 power c, x4 power d, dash 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 dash, xn power m, whatever it is. Okay, like that you need to express them. Okay, then the fifth one is substitute all dimensions, okay, determined at second point at 2 into third equation. Okay, third equation means these all the whatever the dimensions you calculated here, those all things you substitute back into this equation. Then sixth point is, oh, sorry, this is the fourth one. This the fifth point is equate powers of m, l, t, m, l, t of LHS and RHS. Okay, equate it. Then after that, sixth point is determine A, B, C, D values. Then seventh point is substitute A, B, C values into third point equation over. This is what the problem solving procedure. I will follow this only and I will solve the problems. Right? We'll go in the next class, we will solve the problems. Right? Thank you. Welcome back, dear students. In this class, we will discuss about few problems on by Rayleigh's method. Okay. Now see, in a previous slide, we come to know that what are the procedures to follow the Rayleigh's method. The first one is identify dependent and independent variables. Which is dependent, which is left hand side, and which is right hand side, that you need to identify. And after that, write the dimensions of each and every that parameters given in the problem, that it might be your dependent or independent, write all the dimensions. And after that, write the form of Rayleigh's equation. And after that, substitute the dimensions in the equations. After that, equate the powers, calculate A, B, C, D, then resubstitute in the given equation. End of the problem. Okay, now the problem is given here. You can see the time period t of a pendulum depends upon the length L of the pendulum and acceleration due to gravity. Derive an expression for the time period. Here they are telling that this time period is depends on, means dependent. First step is what? Step 1 is what? Dependent variable. Which is the dependent variable? Time is the dependent variable. I will call it as a t is a dependent variable which comes in the left hand side. This is LHS. Right? Now, and it is depending on what? It is depending on the length. Length we will call it as a L, and it is depending on what? It is depending on acceleration due to gravity, that G. This is a comma acceleration due to gravity G. It is depending on that. Therefore, these two terms I will write in the right hand side. First step is over. I identified the dependent variable and independent variables. Then the second step, what it says? Second step is write down the dimensions of the given parameter. Now time represented as a t and the dimension is capital T. This is the dimension of time. And the second one is, second parameter here given is length. This is the length, and we'll call it as a L, L symbol as a L, and the dimension for this length is capital L. And the third one is acceleration due to gravity, acceleration due to gravity, that symbol is G. And gravity acceleration means what? Meter per second square. You can write here meter per second square. Meter means what? Length, and second means time it is, therefore LT raised to minus 2. This is the dimension. Okay, second step is over. I wrote the dimensions of all the parameters, right? Now I will go to the third step. Step 3. Now I will write the form of Rayleigh's equation. Rayleigh's equation is what? T is a function of L and G. T is a function of L and G. Now you can write it as f, a function we will remove it. We will consider a proportionality constant L into G. And here power A, power B you should not forget. Okay. This is what the Rayleigh's form of equation. F of function of first parameter power A, second parameter power B, like that. How many parameters will be there? That many A, B, C, D you will write. But here only two parameters, therefore A and B. Now I will write here A and B. Right? The step 3 is over. Now step 4 is I have to write the dimensions of this one. T dimension is capital T, and this K dimension it won't have because it's a constant, and L dimension is capital L to the power A, and G dimension is L T raised to minus 2 to the power B. In this problem I will solve it very clearly. K, L raised to A, and L raised to B, and T raised to minus 2B. Right? These many, and here T is there. Right? This is what we done, and now we need to go to the step 5. In this step 5 we need to equate the powers. First look at here, we don't have any, actually the fundamental parameters are M, L and T, but we have only T, means here I will write M to the power 0 and L to the power 0. M to the power 0, L to the power 0 and T to the power 1. Right? Now I will equate the things. Then here M is there, and in this side in RHS we don't have any M term, therefore leave it. Then I will come to the power of L. Power of L, LHS side 0 is there, and power of L here A and another one plus B is there. A plus B is the power of L. Right? Now I will come to the power of T. Power of T here in LHS side 1 is there, and in RHS side T is minus 2B. From this I can write B is equal to minus 1 by 2. I got a value of B equal to minus 1 by 2. This B equal to minus 1 by 2 I will substitute here, then I will get A equal to plus 1 by 2. Right? Now over A and B we got. Now going to the step 6. Step 6 I will resubstitute back into my equation. That my equation is T equal to K into L raised to A and G raised to B. See here T equal to K into L raised to A is a 1 by 2 and G raised to 1 minus 1 by 2. This I can rearrange and write, that is K into L by G raised to 1 by 2. This I can represent it as K into root L by G. This is your time over. Right? Now I don't explain, no need to repeat it, because you can just rewind the timeline and go back and see the once again the problem. Okay, now just I can tell here the step 1 LHS RHS are identified, step 2 T L G dimensions are written, and step 3 the form is written, and step 4 the dimensions are substituted, and step 5 powers are equated, then resubstituted back over. Right? Going to the second. In this class we will study what are the types of forces acting on the moving fluid. Okay, say for example, if any fluid is moving, this is a surface, not this one. Okay, if we consider this is a surface, and here if any fluid is moving, this is a fluid, and if this fluid is moving, okay, or otherwise you can consider like this, and this is a fluid moving in this direction, then how many type of forces will be acting on this fluid, that we need to study, so that the model analysis will be easier. Look at here, we have a first inertia force. Inertial force means it is your that whenever you, I think you experience when you are going with a bike, when the brake is applied, then you will feel some jerk in your body, that is what called as an inertial force. When the fluid is moving means there might be some obstacles here, or there might be some resistance here. There you will get some inertial force, that we will call it as a Fi. And we have a second type of force, that is a viscous force. That is viscous force. Viscous force is that one we will call it as a F nu or F mu. And this viscous force, where it will be there? If a fluid is moving like this, then the fluid, we always assume that it is a number of layers will be there, and all these layers are moving, like that we will assume. Then when they are moving, they are not moving with a equally they are not moving, they are moving with a relative speed. Means this is moving, this one layer will be moving faster and the other layer is moving slower. Then the friction between the two layers, that is called as a viscous. The friction between the two layers when they are moving, that is called as viscous, and the force developed in that layer is called as a viscous force. And the third force we have, that is your gravity force. Obviously gravity force, because this earth has a gravity, and the fluid has a mass. Therefore this mass is attracted towards the earth, therefore it will experience some force. That force is called as a gravity force. And the fourth one we have pressure force. Pressure force is when you are pushing the water against the gravity. For example, you will apply some pump to the water to pump the water from the ground floor to the top floor. Then what you do, you will apply some extra pressure. That is your extra pressure, that is your pressure force. Like that we have a fifth one. The fifth one is a surface tension force. That is your surface tension force. Surface tension force, we will call it as a F sigma. And this F sigma, when you will get this F sigma, you will get on the surfaces. If this is a liquid of one density and this is also a fluid, this is one fluid, and air is also a fluid, and air is with other density, and there will be a one layer there, these two are mixing. Say for example, this is a kerosene and this is a water, and there is one layer here, and at this layer the particles are tending to jump, tending to move. Means this surface where these two liquids are mixing, that is an immiscible layer, there you will experience some tension, and that tension force is called as F sigma. And we have a sixth one, that is your elastic force. This elastic force usually we will study in a aerodynamics, where the force when you apply and when you remove that one, the property becomes same. That is your elastic force. This is Fe. Like that we have a 6 type of forces which are acting on the fluid. But as a civil engineers, we are concerned about this inertial force, viscous force, and gravity force and pressure force. These 4 forces are very important for us. And this surface tension force for a chemical industries, paints and all, there they will use, and elastic force, the aerodynamics, they will use that. Right? Now these are all the forces that will be applied on the fluid when it is moving. Then we will study dimensionless numbers. Okay, actually this dimensionless number is a very interesting breakthrough. That is, many scientists, they have did many experiments on a fluid by making a small models, and they have got one conclusion, and they have got one number, and they will be called as a by their names only. For example, Reynolds number is invented by Reynolds, Froude's number is by Froude, Mach number is by Mach, Euler's number. Like that we have 5 type of numbers here. The first one is a Reynolds number, and the second one is a Froude number, and third one is a Euler's number, fourth one we have Weber's number, and fifth one we have Mach number. Okay, now these numbers are what? These are all dimensionless numbers, means they don't have any dimensions. Say for example, if I say Reynolds number is 500, means what? This 500 don't have any dimension. It is not telling any practical meaning. What is the meaning of 500? But by knowing this 500, some property will be assumed, some property will be estimated. How exactly that is estimated? Might be a Reynolds know that one, and he told us also, saying that if the Reynolds number is in between to this and this, the fluid behavior is like that. If the Reynolds number is less than this number, a particular number, then the fluid behavior is like this. Like that he concluded something and he made some experiments. They are called as dimensionless numbers. By using these dimensionless numbers, we have a that model laws. Means in last class I told you that there will be a prototype and there will be a model, and you need to scale down all the parameters which are there for the prototype, that to the model you need to scale down. To scale down them, we need to use some laws. It is not just simply we cannot scale it down however we want. There are some laws. and those laws are called as model laws. And model laws are depending on what? Dimensionless numbers. Those dimensionless numbers are these 5. There are many, but for our fluid mechanics concept in the fluid, when we are dealing with, these 5 are dimensionless numbers. Now we will go one by one. Now we will discuss about Reynolds number. Reynolds number. Reynolds number is denoted as RE, and this is a force ratio of inertial force to the viscous force. And here you can see this is the force and this is the force, therefore force units are cancelled, therefore this is called as a dimensionless formula. Now if I take this inertial force, that inertial force is mass into acceleration, and this mass is what? Rho into volume, that is the density into volume, and this is the velocity by time. Here you can see volume by time. Volume by time means what? It is the discharge. Discharge is equal to what? Area into velocity and another velocity. Therefore I got area velocity square. This is your inertial force. Then we have viscous force. That viscous force means what? You already know that formula. Viscous force means what? Last year you studied this tau is equal to mu into du by dy. This is the Newton's law of viscosity, and this tau is what? Force divided by area, and this force is the viscous force. And then what is that? F equal to tau into area, and what is this tau? That is your mu into du by dy into area. Then this is a mu, and this velocity it is, and this is a y. Dy means it is a length it is, and this area is length square. Therefore I can have mu, v and L. That is your force. Which force it is? Viscous force. Then I got a Reynolds number equation. That is Reynolds number equal to rho a v square divided by mu v into L. Okay, no? Then further what I can do? This rho, this area means again L square, and this is a v square divided by mu into v into L. Then 1 L cancel, 1 v cancel. Therefore Reynolds number is equal to rho L v divided by mu. This is your Reynolds number. This is a dynamic viscosity. If you want a kinematic viscosity, then this rho will come down, then mu by rho is your kinematic viscosity. Then Reynolds number will be L into v divided by mu. You can use these two, any of these two, you can use it for Reynolds number. Okay, now we'll go to the second dimensionless number. That second dimensionless number is Froude number. That is your Froude number. Froude's number. And the Froude's number means, this is a definition given by the Froude, that is the Froude's number is equal to under the square root the ratio of inertial force to the gravity force. Then again inertial force, in the last slide I already derived, rho a into v square, and the gravitational force is what? That is your mass into acceleration due to gravity. Therefore here mass means rho into volume into gravity. Okay, that I will substitute here. That is your Fi is a rho a v square, and divided by, this is rho into area, L cube I can write it. This is L cube into G, that is volume means L cube, and further this rho cancel. Further I will get area means it is a L square v square divided by L cube G. Then again L square and L cube cancels, then it will be v square divided by Lg and their root. This is your Fr, and you can simplify it like Fr is equal to v divided by root Lg. Root Lg is your Froude's number. Understood? Very important definition. And the third one we have, and third dimensionless number we have Euler's formula, Euler's number. And this Euler's number is denoted as a E, and this is the ratio of Euler's number is the ratio under the square root, that is the inertial force to the pressure force. And inertial force is what? That inertial force already derived, rho a into v square, and we have a pressure force. Okay, this pressure force means what? That is the pressure into area. That is your pressure into area. This one only we will substitute here, that is square root of rho a v square divided by pressure, small p, it is small p into area. Then area cancels, then I will get v square divided by, I can write it p by rho. This one p by rho I can write and put the square root. Then v this Euler's number I will write it further like V divided by square root of P by rho. This is the fashion which is maintained by the Euler. Therefore the rho is brought down and P by rho will be written. This is your Euler's number. And we have a fourth one. We have a fourth one, that is a Weber's number. Weber's number. According to Weber, he defines this number as WE is equal to the ratio under the square root of inertial force to the surface tension force. And this inertial force already derived, that is the rho A into V square, and this surface tension force, that you can define it as a surface tension into length. Surface tension into length. Okay. Then we will substitute here, that will be rho A V square divided by surface tension into length. Then this A I can write it as a length square, rho length square V square divided by sigma into L. Then 1 L cancels. Then I will get a Weber's number as V divided by square root of sigma by rho into L. Okay. This is what the fashion maintained by the Weber. We will write the everything downside and we will maintain this V at the top. This is your Weber's number. This is also dimensionless number. And the last one, we have a fifth one, the Mach number. And this Mach number is defined by the Mach, and that is denoted as a M. And this M is a ratio under the square root of inertial force to the elastic force. Inertial force means, again you know, there is a rho A V square, and this elastic force we will get it like a elastic stress into area. That elastic stress we will call it as a K. Actually this K you can call it sigma also, but K no problem. This area I will consider it as a length square. Then substitute here rho A V square divided by FC is what? K into L square. This area is also L square and this is also L square. Cancel. Then you will get V square divided by K by rho. Then this will be nothing but V by root of K by rho. And this is your Mach number. And according to Mach, he will define this one. He will make it very simpler. That Mach, he says that V divided by C. Then we asked us, then from where the C got? Then he said that C means it is a K by rho. K by rho means it is a velocity of a sound. This is velocity of the sound, and this is the velocity of the article. Understood? These are all dimensionless numbers. In the next class, we will see model laws by using these dimensionless numbers. Thank you. Okay, now we will discuss model laws or similarity laws. We will discuss model laws or similarity laws. Means to scale down of the prototype parameters to the model parameters, we need to use these laws, model laws. The first model law is Reynolds model law. Reynolds model law. The second one is Froude's model law. Froude's model law. And the third one is Euler's model law. Euler's model law. And the fourth one is Weber's model law. And the fifth one is Mach model law. Okay, these are there. For your information, this Reynolds model law, we will use it for pipe flow, or where the viscosity is predominant. For example, when a ship is moving inside that submarine is moving inside the ocean, then when it is moving, then there will be this movement is or resistance offered by that ocean water is again depending on the viscosity. Okay, or otherwise aeroplane moving under this aeroplane is moving under inside the air atmosphere, then this is also comes under Reynolds model law. Okay, means what? Here pipe law or submarine or aeroplane, when they are moving, then viscosity parameter is predominant, therefore Reynolds model law we are going to use. Then Froude's model law, we are going to use it for open channel flows. Open channel flow, that is your sanitary flows or river flow or canals or spillways, dams. These are all comes under when you make a prototype and model of this one, then you will use the Froude's model law. Then Weber's model law, and these are all for as per the syllabus, these are all not included for you. And this Euler's model, I can say that here pressure is used, and Euler's model also sometimes we can use it for pressure flow. In the pipe flow we can use this one, and but Weber's model where surface tension is a predominant, chemical industries they will use this one, and Mach model law aerodynamics they will use this Mach model law. For civil engineering are concerned, we will use Reynolds model law and Froude model now. Okay, that's why for your syllabus also we need to study all these 5, but we have problems. We need to study specifically problems on these 2 laws. Okay, then we'll go one by one. Then in general, what these laws tell us is, if I calculate the dimensionless number for a prototype, and the same dimensionless number if I calculate for a model, then these 2 dimensionless number must be same. If I calculate Reynolds number for the prototype, if I calculate the Reynolds number for the model, and these must be same, and like that for all other numbers also. Okay, now when you maintain this dimensionless number for the prototype and model same, then considering these all, then all the ratios with respect to this Reynolds number, then all other ratios will be maintained. Means all other similarities like the geometric similarities or kinematic similarities, dynamic similarities, they all maintained based on these model laws. Now we'll go to the first one, Reynolds model law. Reynolds model law. Reynolds model law. As I already told you that this model law will be used for the application will be for the pipe flows and submarines moving under the water, that is the ocean, or aeroplanes moving in the atmosphere. Okay, for these problems we can use this Reynolds model law. And in this Reynolds model law, let us consider the density of the prototype is rho, and velocity of the prototype Vp, and length of the prototype is Lp. Then viscosity of the prototype if I call mu p. Then the correspondingly for the model I will write rho m, Pm, and Lm and mu m. Okay. Then as per the law, rules of the law, that is the Reynolds number for the prototype must be equal to Reynolds number for the model. Right. Then what is the Reynolds number? Basically we know this one as a rho V L by mu. This is the formula for the Reynolds number. Like that for the Reynolds number for the prototype and Reynolds number for the model, they must be equal, means rho p Vp Lp divided by mu p is equal to rho m Vm Lm divided by mu m. And I will rearrange the terms here, rho p by rho m and Vp by Vm and Lp by Lm whole divided by mu p by mu m. That must be equal to 1. Then here you can see here that rho p by rho m is density ratio, velocity ratio, length ratio divided by viscosity ratio is your 1. This is your 1. It should be 1. Understood? This if you satisfy, then you are applying the Reynolds model law, and your model will work out easily. Right? Then by considering this one, there are other parameters which are not included here. If you want velocity, you have here, length you have, then these are all you know. But some other parameters, like if you want to scale down the time, then what need to do? Then time means what? First we need velocity is equal to distance divided by time. Then time is equal to what? Velocity divided by, length divided by velocity. Then time ratio will be equal to length ratio divided by velocity ratio. This we have to maintain. Then how to get this length ratio? Length ratio if you assume, then velocity ratio you cannot assume. You have to calculate that velocity ratio by using this equation, by knowing some other parameters. By knowing other parameters, you have to calculate velocity ratio from this equation, and that velocity ratio I am going to substitute here. And what is this Tp by Tm? Because time ratio is a Tp by Tm. Knowing the time of the prototype, you can design the model time, or knowing the model time, you can get the information of prototype time. Like that. Then this is a time. Like that, if you want to scale down the acceleration, then what is the basic formula for acceleration? That is velocity by time. Then I can have acceleration ratio equal to velocity ratio divided by time ratio. velocity ratio by time ratio. Now velocity ratio you have to get it from the Reynolds number equation, that is the previous slide, and time ratio you have calculated here. That time ratio you need to use and calculate the acceleration ratio. Understood? Like that, if you want a force, if you want to scale down the force, then what is the basic formula for the force? Force is a mass into acceleration. Then what is the mass? Mass is a density into volume. Volume means L cube, and acceleration, this is the acceleration. Then force ratio will be is equal to what? Density ratio, length ratio cube, then acceleration ratio. And acceleration ratio you have to substitute here. As I said that length ratio, if it is assumed, then that's fine. Then this rho ratio, that is the density ratio, also you should get it from here. Okay, then you can have the force ratio. Then the force ratio means what? Force in the prototype to the force in the model. Then whichever one among these, if you know one, the other can be calculated. Understood? Now this is your Reynolds model law. Not only this one, even if you want to do that scale down the discharge, that is area into velocity, like that many parameters will be there. By using their basic equations, you can scale down to your required parameter. Right? Now we'll go to the second model law, that is a Froude's model law. Froude's model law. Froude's model law. Then basically what is the Froude number? Froude number is a V divided by root of LG. Froude number. Then Froude number will be definitely Froude's ratio is equal to this Froude number. Froude number for the prototype will be equal to velocity in the prototype divided by root of length in the prototype and gravity in the prototype. But here usually what we do, the model and the prototype both are on this earth only, then earth has a gravity same, then this 9.81 whatever the acceleration due to gravity is there, this will be applicable same for model and same for prototype. Therefore we cannot change here. Therefore I will consider prototype G and model G same. Then I can remove this one. Say for example, this is for model, and F for the prototype is equal, model is equal to model divided by L M into GM. Now what the law says, what is the generally the model law says, that is Froude numbers for the prototype and Froude number for the model must be same. Means what? Vp by root Lp is equal to Vm by root Lm. This must be maintained, and further you can reduce like this: Vp by root Lm is equal to Vm divided by root L, Vp by this one and M. Now Vp by Vm we can bring at one side, and a root of Lp by Lm. Now as I said that always we will assume this one Lp by Lm based on our space, okay, available in the laboratory. We will always assume this one. We will always assume this Lr. Then you will get a Vp by Vm is nothing but your Vr, velocity ratio, that is your length, root of length ratio. Now you got a velocity ratio which is calculated based on length ratio. Then by using this one you can go further to find out the time. Then what is the time? Time is the length divided by velocity. Then if you want a time ratio, that is your length ratio divided by velocity ratio. Then what is your length ratio? Then velocity ratio is just we calculated here, that is your root L ratio. Then this numerator I can write it like a root Lr and root Lr again divided by root Lr, then cancels. Then what is this time ratio? Time ratio is again root Lr. Now you got velocity ratio as this much and time ratio as this much. By using these two you can calculate acceleration ratio. Acceleration is what? Velocity divided by time. Then what is the velocity ratio? Root Lr. What is the acceleration ratio? That is also root Lr. Therefore you are always getting acceleration ratio as a 1. Means for the prototype and for the model, acceleration is same you need to maintain, not similar. You need to maintain same. That is your acceleration for the prototype and acceleration for the model, you need to maintain same. Right? Like that, if you know these all parameters, further you can go as a force ratio. That force ratio is equal to what? Mass into acceleration. Again, that is mass is a rho into Lr cube, that is a rho r into Ar cube. Ar. Okay. Here what all you know? You know Lr, you know Ar, and you can consider this rho sigma r, this rho r also, density ratio. By knowing these are all, you can calculate the force ratio. Understood? Means by knowing some parameters, that is your Reynolds number or Froude number, and by using the law, that is your Reynolds number for the prototype and model, Reynolds number for the model, or Froude's number for the prototype and Froude number for the model, equate them and you will get some ratios. There you always assume the length ratio, and by knowing the length ratio you substitute and get other parameters by using basic equations. That's it. Understood? Now like that we have a third law. Third law is what? That is your Euler's law. Euler's model law. Euler's model law, again the same thing, that is Euler's number for the prototype must be equal to Euler's number for the model. Then what is the Euler's number? Basic equation for Euler's number is V divided by root of P by rho. Then you will write it like velocity ratio divided by pressure ratio divided by density ratio must be equal to P it is. Velocity P and P must be equal to Vm divided by square root of Pm divided by rho m. Right? Means you will get these are all ratios. Here among these you can assume one parameter and go ahead with the other. Like that we have a fourth law, that is your Weber's law. Weber's law, what it says, that is the same. Weber's number for the prototype must be equal to Weber's number for the model. Okay. Then what is the basically Weber's number formula? Weber's number is equal to V divided by square root of sigma divided by rho into L. That is velocity for the prototype divided by surface tension for the prototype divided by density of the prototype, length of the prototype must be equal to velocity of the model whole divided by surface tension for the model, density of the model and length of the model. And this condition you need to satisfy considering the Weber's law. And the fifth one we have a Mach law, Mach model law. Mach number basically is what? M equal to, that is V by C. Then you should have, that is Mach number for the model prototype and Mach number for the model must be same. Then what you need to do, Mach number means that is a velocity for the prototype and C is a constant, and this C sometimes it again varies because sound of the that is the speed of the sound depending on the quality of the air and media. Okay, the speed of the sound may be faster in the water and slower in the air, again faster in some material like steel and slower in the water. Like that the speed of the sound is also depending on the media, therefore this is also not constant. Like I will consider the speed of the sound in the prototype and velocity of the model and the speed of the sound in the model, I will consider this law. Okay, like that we have a 5 model laws, and next class we will consider Froude's model law and Euler's model law and we'll solve many problems. Okay, thank you.